today the title of my talk is Synthesis of Bimetallic Iridium Nanoclusters and their application in the degradation of azo-dyes. As we know that metal nanoclusters are catalysts of choice. They are, due to their fascinating properties, green nature, ability to catalyze selective reactions at low temperature, increase surface to volume ratio, applications in several areas such as microelectronics, optoelectronics and photocatalysis. These noble metals are used as nanoclusters due to their enhanced catalytic activity, high stability and minimum poisoning effect from external sources. Noble metal nanoclusters are in continuous and ever increasing demand. The other reason for their use is their properties and uses can be changed by changing the size and organization of the metallic nanoclusters in crystal lattice and chemical nature of the microenvironment surrounding the nanocluster. Thus, why we have synthesized these bimetallic nanocluster, or what is the need of synthesizing bimetallic nanocluster? There are various noble metals as platinum, ruthenium, rhodium and iridium, and their nanoclusters have been synthesized, but these metals are very costly and due to their high cost, their use is very limited, but their catalytic activity is very good. Thus, there is need to lower these metal loading. That is, the demand should be low. So, we have taken the approach to synthesize the bimetallic nanoparticles because it is reported that the bimetallic nanoparticles are more effective in action. They act like an alloy. The durability and activity of bimetallic nanoparticle is much better than monometallic. They reduce the expense of single metal. Thus, we have chosen iridium as the noble metal and synthesize the bimetallic nanoparticle. Iridium is a good catalyst, has higher stability, selectivity and under high different reaction conditions, it is less expensive as compared to platinum. So, our purpose is to synthesize the bimetallic nanoclusters of iridium. The other metals which are chosen to form the bimetallic nanoparticles are tin, lead and copper, and then the second purpose was to study the effect of other metal on the catalytic activity of the monometallic iridium nanoclusters by using the reaction of the oxidation of some azo dyes by hexacyanoferrate 3 ions in aqueous alkaline medium. So, the first part is the synthesis of bimetallic nanoclusters. The bimetallic nanoclusters were synthesized by modified polyol method using polyvinyl pyridine as protecting agent and ethylene glycol as the reductant. These are the materials and techniques used for their synthesis, and this shows the method of preparation of the bimetallic nanoparticles. Initially, the color of the solution was light yellow, and after 1 hour reflection, it converts to the blackish brown color. Then the synthesis of these bimetallic nanoparticles was carried out by spectrophotometrically, and it is observed that these spectra, initially there is a peak at around 205 nanometer, and with the passage of time this peak shifts to the higher wavelength side. So, this shows that there is a reduction of metal occurring, and then finally we, after reflection, we have note down their spectra. This green spectra is for the bimetallic nanoparticle. So, initially it was at 205 and then it is shifted to 224 to 279 and 257 nanometers. So, this is for iridium tin nanocluster, this is for iridium nickel nanoclusters, and this is for iridium copper nanoclusters. Now, after synthesis of these nanoclusters, we have characterized these nanoparticles by X-ray diffraction, transmission electron microscopy, energy dispersive X-ray spectroscopy, X-ray photoelectron spectroscopy. This XRD tells us about the amorphous nature of the particles, and these are the XRD of monometallic iridium, these are of monometallic tin, and this is for bimetallic iridium tin nanoparticles. And if we compare these spectra, we find that initially the particles are more crystalline as compared to the bimetallic nanoparticles. Again, the shifting of these peaks from this position to this new peak, this shows that there is some alloy type formation between the two metals. And same is the case with iridium nickel and iridium copper nanoclusters. Then the size of the nanoparticles was determined by transmission electron microscopy, and it shows that this TEM images shows that the particle size for iridium tin is 2 nanometer, and this is for 4 and this is for 3. So we can say that the particle size is between 2 to 4 nanometer. Then EDX was performed, and EDX shows that the nominal atomic composition which we had initially taken was 89 is to 10.8%, and the same is for the calculated by the EDX. Then XPS is carried out to study the oxidation state of the metal nanoparticles. This is for the XPS. This is XPS for the iridium tin nanocluster, and this shows the one is for carbon 1s spectra. It shows that the presence of carbon in 1s state, and its presence is from the polyvinyl pyridine, and this iridium is in 4s 7 by 2 and 4s 5 by 2, and these two peaks corresponds to the iridium 0 state of the iridium, and this iridium 3d 5 by 2 and tin 3d 5 by 2 and tin 3d 3 by 2, this peak is deconvoluted, that is it shows the presence of tin in the form of tin oxide, that is SNO and SNO2, and it is not easy to say that it exists in the form of SNO or NSNO2 because the energy difference between the two is very less. The same is the case with the iridium copper and iridium nickel. This is for nickel and this is for copper. So first we have synthesized the bimetallic nanoparticles. Now we want to study that when we have mixed the other metal to the noble metal iridium, which is very costly due to its rare existence, what is the effect on its catalytic activity? Is it increases its catalytic activity or it decreases? So for this purpose we have chosen the degradation of dyes which occur in the water of dye effluent as a pollutant, and their degradation by hexacyanoferrate 3 ions in aqueous alkaline medium, and the study has been carried out by kinetic method. We know that the dyes, azo-dyes, are the largest and most versatile class of dyes used in the textile, cosmetic, pulp, paper, food and pharmaceutical industries. They have unique property of brilliant shades, cost and simple manufacture. They contain one or more azo groups bonded to aromatic rings which are mostly substituted sulfonated aromatic rings. And we have selected 3 dyes. One is acid orange 5, other is acid orange 10, and third is acid orange 27. One is monosulfonic, second is disulfonic, and third is trisulfonic. Then the experimental conditions that are the oxidation kinetics of the azo dyes has been carried out is kinetic spectrophotometrically at the lambda max of the reaction mixture at optimum pH and constant temperature at different concentrations of one reactant, keeping the concentration of others constant. And these are the conditions which are set for the experiment. Then to set the pH, first of all we have set the pH by varying the pH in the range of 6 to 10, and it is found that in case of acid orange 5 and acid orange 10 it is 8, and in case of acid orange 27 it is 10. Then the effect of oxidant, that is hexacyanoferrate 3 on the reaction rate, has been studied, and it is found that in all the cases, that is in case of all the 3 types, it follows first order kinetics. But and we have also studied these effects on this black line shows the reaction uncatalyzed, this red line shows reaction in presence of iridium monometallic particles, and this green line shows the reaction in presence of bimetallic iridium nanoparticles. So this shows that the rate is increased with the bimetallic nanoparticles. Then we have studied the effect of substrate, that is dye concentration of the reaction rate, and it also shows the same type of result, that the reaction rate increases with the substrate concentration. Then the effect of catalyst concentration also studied, and to study the catalyst concentration, first we have studied the reaction in presence of iridium precursor, that is iridium trichloride as such is used, then iridium monometallic catalyst is used, then iridium tin bimetallic catalyst is used sorry, and again it shows that the reaction rate increases. This is in presence of precursor, this is in presence of monometallic, this is in presence of bimetallic nanoparticles. So if we compare the percentage degradation of all these three dyes oxidation in presence of precursor, iridium trichloride, iridium nanocatalyst and iridium tin bimetallic nanoparticles. So we found that the reaction rate is maximum in presence of bimetallic nanoparticles. That is, bimetallic other metal has the synergistic effect on the reaction rate of the degradation. We can compare that. We can see that in this case, if 30% degradation, the precursor requirement is around 16 into 10 to the power minus 7 moles per liter. But for the same reaction, the requirement of monometallic iridium is 12.5 into 10 to the power minus 7 moles per liter. But in case of bimetallic nanoparticles, this is only 7.5 into 10 to the power minus 7 moles per liter. So we can say that the cost of the catalyst is decreased to a large extent and reaction rate is also increased. These thermodynamic parameters are also calculated by carrying out the reaction and at 4 different temperatures, that is 42, 40, 45, 50 and 55 degrees centigrade. The energy of activation, delta H, delta F, these are calculated, and these parameters, if we compare energy of activation, we found that this is the EA for uncatalyzed, this is for nanocatalyzed and this is for bimetallic. So this also supports our work that the rate of degradation in presence of bimetallic nanoparticles is more than the monometallic or the molecular iridium particles. The other part of this technique is to investigate the economy of the present method, that is bimetallic nano were recovered and reused for the 3 consecutive cycles, because we know that these are very costly. So we have recovered and found that these nanoparticles can be recovered up to 3 consecutive cycles, and this is confirmed by the X-ray spectra. This data show that this is before recovery, this is the rate of reaction, and after first cycle, this rate decreases with the number of cycles, that is from first to third, this rate decreases from 5.6 to 2, and we have determined the approximate particle size by XRD. So this XRD also shows that the particle size increases with the consecutive cycles. This may be due to the agglomeration of the particles. Again, same is the case with the other dye, and the same type of study has been carried out by using the particles of iridium copper and iridium nickel. We have also I have also compared the reaction rate with the catalyst concentration. This shows the reaction rate in presence of iridium copper. This blue line shows in presence of iridium nickel. This is in presence of this is iridium monometallic. This is iridium copper, iridium nickel, iridium tin. So we can conclude that the catalytic activity of bimetallic iridium tin is better than the iridium nickel and iridium copper. Then the product of this method is also analyzed. We know that the azo dyes are the hazardous substances, and it is where they are resistant to chemicals. It is very difficult to degrade them. But by this method, we found that these methods are characterized by LCMS, and these all the products are generally simple acids. So we can say that the azo compounds have been converted into simple, less hazardous compounds. So finally, we conclude that the bimetallic metal nanocluster synthesized have been found exceptionally efficient catalysts for the oxidation of studded azo dyes, and the second is the addition of other metal with iridium nano shows the synergistic effect on its catalytic activity. Thus, synthesized nanoclusters reduces the iridium noble metal loading and makes them potential candidates for dye degradation technology.